All right, let's get started. Again, welcome to everyone who's joined us today. I'm Samantha Link, and I'll be moderating today's webinar on Robotic Solutions for Asset Reliability. As we go through the presentation, all attendees will be muted, but please be sure to send us questions through the Q&A feature located at the bottom of your Zoom screen. I'd like to go ahead and introduce our presenter today, David Vatz. David is the Pulp and Paper Industry Manager at Gecko Robotics and has been in the pulp and paper industry for the past couple of years. David has become a huge proponent in helping mills understand robotic capabilities in the industrial space, as well as data utilization for inspections. A native of Pittsburgh, David graduated from the University of Pittsburgh. Let's all welcome David.
Hi, everybody. Thanks a lot for joining us today. I first wanted to start off by just saying I hope everybody is staying safe and healthy given what's going on right now. I know it's weird times for all of us in the industry. I haven't been on a mill site for about 4 weeks now, which is really strange. I know I've met some of you in person at the mills, and hopefully soon we'll get back to normal and we'll be able to meet in person again. But I wanted to welcome you. And as Sam mentioned, please feel free to submit questions through the Q&A feature. Sam will be interrupting me with questions throughout the webinar. So if there's a question that you have that's related to one of the slides, feel free to post it and she can ask it to me during. And then we'll also have some time for Q&A at the end. So what I wanted to start with here is just a little bit of discussion about what we hope everyone will learn today on the webinar. So what we'll start with is going over the different types of inspection robots that are out there. These might be some things you're familiar with, might be some new things. We'll talk a little bit about the advantages and disadvantages of robotic inspections versus manual inspections. We'll go through a couple of different case studies of work that Gecko Robotics has done at paper mills, including recovery boilers and also batch digesters. And then we'll talk a little bit about what the future holds for robotic inspections and where the industry is going. So we'll jump right in here with the different types of robots that are out there that do inspections right now. And so we'll go here from left to right, top to bottom. In the top left there is the Gecko Toka 4 crawler robot. So this is a robot that will climb up the walls of tanks and silos and boilers and take readings while it does that. To the right of this is the Helios 2 drone, which I know many of you probably use at your mills today. It can fly into and around assets. And then at the bottom is a pipeline pig. And so we'll talk a little bit more about some of the details of those different types of inspection robots. So the first one we looked at was a crawler robot. So crawlers are designed to climb up assets and collect NDT readings and imagery as they climb up. These are robots that typically require adhesion to the surface somehow so that they can climb up the assets, and they'll take those readings as they go. The second type was drones. Drones are used in a lot of mills right now for manual and automated flights in and around assets. And they're often used to go into places where a human can't go. So into, say a boiler that hasn't been cleared for confined space entry. And as of right now, the amount of NDT readings that drones can take is relatively limited. So some drones can take maybe spot UT readings here and there, but for the most part, drones are just being used to collect visual imagery at mills currently. And then the final type that we went over was pipeline pigs. Pipeline pigs are a specialized type of robot that's used a lot in the oil and gas industry, and they were originally designed to perform cleaning on the inside of pipelines. However, recently they've been made more smart, so to speak, by adding sensors so they can collect NDT data and then also visual imagery as they go.
Hey, David, we have a couple questions in here. So first, can you explain how a crawler would normally adhere to surfaces?
Yeah, sure. So I'll give you the example of the Gecko crawler. Right now, the way the Gecko crawler adheres is through magnetic wheels. So our robot can climb up any ferrous surface, like a carbon steel tank or a carbon steel boiler walls. However, there are adhesion methods that are being worked on to allow climbing up of non-ferrous surfaces, such as stainless steel.
Great. And then for crawlers, someone wants to know that they're assuming that it's for tanks that are out of service, but they're not sure if it could be used when the tank is still in service.
Yeah, so crawlers can absolutely be used on in-service tanks. So we do a lot of inspections with crawlers of online tanks. It's actually one of the nice benefits of it. You can crawl up the outside of a tank while it's still online and collect NDT readings without taking the tank down. So even on hot surfaces, on, for example, black liquor tanks that are 150, 160, 170 degrees, you can still take readings on those. Of course, you can't do the inside of the tank if there's still stuff in it. The robot that we have, at least, is not submersible. But there is some work being done to make the robots submersible in the future.
For drones, how do you categorize visual data collected by them?
Yeah, so I think this is an interesting question. It's one of the challenges with drones right now is that you can collect a lot of visual information with a drone, but it's really just going to be videos that someone's going to have to go back and look at. And so there's a lot of work being done right now, both at Gecko Robotics and also with a lot of the drone companies, to be able to both geolocate drone imagery so that you know where it's being taken. So you can do this outside with GPS, but inside of a boiler, you might not have a GPS signal. And then there's also work being done with AI and machine learning to be able to look at images and categorize those images and maybe even identify defects. So there's a lot more to come on that, I'd say, in the future.
Great, thanks. That's all we have for now.
All right, so we'll hop into some of the challenges of manual inspections. And I'm sure many of you who are on the line right now are folks who deal with inspections at the mills. So you understand a lot of the challenges with manual inspections. The first one being the issue of downtime. So manual inspections are not always fast. They can often take several days or even weeks to complete with larger assets. And because they do take a lot of time, you're often limited in the amount of scope and the amount of data that you can actually collect in that period of time. In addition to that, especially with what we're seeing with the coronavirus outbreak, the idea of having large inspection teams on site for something like a boiler outage is a real potential challenge with manual inspections. The larger your inspection team is on site, the more potential there is for injury and right now sickness as well. And in addition to that, with manual inspections, you often need to erect scaffolding or use rope access, and you need to put people into confined spaces to get readings. The next item here is the potential inaccuracy of it. With manual inspections, you're often relying on the skill and knowledge of a human operator. And so if that human operator maybe was trained incorrectly or they are not as familiar with the asset, they might not be able to get good readings for you. And in addition to that, the readings that they get might not be easy to trend year over year because they might be collected in a different way every time. And then the final challenge here, and we've got a visual that's going to go along with this, is this idea of having to be reactive with your repairs. So not collecting enough information can lead to reactive repairs rather than proactive repairs. And I'll show you guys a quick visual on this. So this is a great example of a boiler that we recently did a scan on, actually just like 6 days ago. And it's a great example of reactive versus proactive repairs. So if you look at the north left side wall and the big green area in the middle, that's an area where the plant had performed a repair. But it's clear from the scan that Gecko did that they actually missed a large area of concern. And this was because they didn't have enough information to actually proactively make those repairs. And so instead, they're left with the possibility of equipment failure that could lead to unplanned downtime.
So what actually makes manual inspections inaccurate?
Yeah, well, so there's a couple of things that you have to be aware of with manual inspections. The main one, and this will be specific to ultrasonic thickness readings, is that typically the people who are going out there and actually taking these ultrasonic thickness readings, they're using a D meter that's giving them a 3-digit number for a thickness. And so they're not actually looking always at the ultrasonic thickness signal. And because of that, they're kind of relying on the meter taking the right reading for them. And sometimes if they see a low reading, they might say, well, oh, that doesn't really make sense. I'm going to keep hunting until I find one that's right. With robotic data collection, where you're collecting the actual signals and you're collecting a bunch of bulk information, you can ensure that some of these low spots that might be missed by human inspectors aren't missed with robotics. All right, we'll move on here to some of the disadvantages of robots. Obviously we're big believers in robots here, but they don't come without their disadvantages. And so we'll talk through some of those here. The first one is that robots tend to be highly specialized. So we looked at the images of the different types of inspection robots at the beginning. All of those were really designed for one specific goal. With a human inspector, you can kind of throw them at a bunch of different challenges and they can just figure it out and jump around different obstructions and things like that and still get readings. Whereas with a robot, you have to be a little bit more prescriptive about what is the problem that you're trying to solve and how will the robot solve that problem. And kind of following on that, robots can have some difficulty with unusual or obstructed assets. Things like stiffener bands can get in the way, catwalks, other obstructions that might be blocking the way from getting readings. The next item here is cost. On a cash basis, robotics tend to be high upfront purchase price or the cost of paying for robots as a service. The good thing with this is that the price of robotics has come down really substantially. Even in the last year here at Gecko, we've seen our prices drop about 30 or 40%. And that's because as the robotic technology continues to advance, companies that produce these robots are getting to a point where they're able to produce them at scale, they have better processes in place, and they're able to collect data more efficiently. And then the final disadvantage is that robotics require specialized operators, people who are operating these robots, whether it's a drone or a crawler robot, they need to really understand how to use the equipment. So it does require people who have a good understanding of that. We've heard from a lot of the different mills out there that stuff like drone flights are required to be done by people who actually have certification in flying those drones. And I know a lot of mills are now setting up drone programs for that purpose. So that's some of the disadvantages of robotics.
Can you talk a little bit more about how much it really costs to perform an inspection with a robot?
Sure. Yeah. It's a good question. There's no one simple answer to that. Obviously, the cost of performing an inspection with a robot really varies from asset to asset. But I would say there's a number of different ways that clients are saving money with robotics. And so I'll talk through a few of those. So I'll give an example of a tank inspection that we recently did at a paper mill where they were concerned that they needed to replace the entire floor of the tank because you could look at this tank floor and you could see it had some serious problems. So we ran an inspection on the tank floor where we collected a bunch of data on 100% of the tank floor. And based on the result of that, we were able to save the mill about $20,000 on the tank floor repair because instead of them having to repair the entire floor, we were able to identify an area of serious concern that they needed to repair, and then the rest of it was actually in okay shape. And so this would be something that would be really hard to find with manual inspection because you wouldn't be able to collect enough data to really understand. And then the other ways that customers can potentially save money with robotic inspection is through reduced need for infrastructure, such as scaffolding. So robotics might have a higher cash cost than a manual inspection, but when you factor in that you don't have to scaffold as much, you can often save money from that. The idea of reduced downtime, so you could maybe shorten the length of an outage by getting robotic readings faster than manual inspection. And then also having more targeted inspection frequencies. So instead of inspecting something every year, maybe you inspect it every 2 or 3 years, but with higher density data. And that allows you to save money on having fewer inspections.
Do you have a cost difference between scaffolding versus robotics inside of tanks?
Sorry, can you repeat the second part of that question?
Yeah, so do you have a cost difference between scaffolding versus robotics inside of tanks?
Yeah, and again, it really does depend on the specifics of the tank project. However, a lot of times the cost of a robotic inspection can end up being less than just the cost of scaffolding a tank. And we see this in boilers as well. There are some boiler jobs that we do where the cost of scaffolding the entire boiler is more than the entire cost of our inspection. So It really depends on the specifics of the job, but a lot of times being able to eliminate that scaffolding will completely pay for the robotic inspection.
So the crawler robot you talked about, can the crawler get reliable data without cleaning for a recovery boiler?
Yeah, so the answer is we'd probably have to see the condition of the surface first to be able to give a real answer on that. But for the most part, our expectation is still that there would be a water wash done on a recovery boiler prior to us putting the robot in. There doesn't need to be, additional cleaning or grinding done like you might have to do with manual inspection. However, it would need to be just water washed prior to us coming in for a recovery boiler.
Great. And then is there any work on an eddy current probe for looking for cracks?
Yeah, we'll talk about a little bit with that in the future. It's something that we're looking at least with our robot. We have the ability to attach different sensors to our robot. So currently we can put UT thickness reading sensors and then also magnetic induction sensors on it. Eddy current is something that's been discussed for the future, for sure. All right. We'll hop on here to the next slide, the advantages of robots. And so we started talking about this a little bit with some of the answers to the questions here, but the main advantages of robotics is bulk data collection. So robots can gather about 100 times more data and sometimes even more than that than manual inspections can in the same amount of time. This leads to the ability to have really high resolution data on whatever it is you're looking at, which can help you make decisions on it. So in addition to collecting a lot of data, robots can often collect it significantly faster than manual. And an example of a recovery boiler, oftentimes we can shave 2 or 3 shifts off of the typical NDT window that you have for a recovery boiler. And again, a lot of this depends on your specific scheduling, but oftentimes we can cut 2 or 3 shifts off of it. And a good way of thinking about this is a human inspector can collect, say, 200 to 250 readings per hour when we're talking about ultrasonic thickness testing. Our robot can collect about 270 readings per second. So you're talking orders of magnitude greater information gathering capability with a robot versus a human inspector. Additional advantages here would be safety. With robots, you can limit the use of scaffolding, which we've talked about. You can limit the use of things like rope access. And you can also limit the number of people that are on site during outage windows and things like that. A typical outage for a recovery boiler, we're seeing anywhere from 20 to 50 inspectors. For robotics, we would put maybe 4 to 6 inspectors into a furnace for that exact same scope. So it's a significant difference where we're able to do an inspection with about 75% less human inspectors on site. And then in addition, robots can often go where people can't go. So we talked about this a little bit with drones. A drone can fly into a boiler that hasn't been cleared for confined space entry. A crawler can get into spaces that are smaller than a human inspector could get into. So a lot of times these robots can kind of go places and do things that humans can't. And then finally, repeatability is a big factor with robotics. A robot's never going to get tired. It's never going to come in hungover. It's always going to get the job done. And it's going to do the same thing year after year, no matter what. So your data collection method, you can be certain that it's going to be exactly the same year after year, and you'll be able to repeat that inspection over and over again to get good trending data.
So scaffolding tends to be a pretty large amount of the cost of inspecting assets. Can robots really inspect all assets without scaffolding?
Yeah, I would say robots can inspect a lot of assets without scaffolding. There are some times where you might need to, erect a limited amount of scaffolding. So a great example of this would be in a recovery boiler. There are going to be manual readings that still need to be taken around airports and liquor guns and things like that. And so usually what we see in a recovery boiler is mills will scaffold up to the tertiary airports, and we will run the robot on that lower section, but also then above the scaffolding up to the nose arch or the maintenance beam without any scaffolding. On tanks, we can usually do them with no scaffolding. On digesters, we can do them with no scaffolding. So it really depends on the specific asset, but we can usually either limit the scope of scaffolding significantly or do it with no scaffolding at all.
Gotcha. So what's the minimum clearance for the crawler to travel up a shell? For example, to scan a digester shell that has a liner of plates covering access to the over the outer shell. So just as a note, the scan is from the inside while a maintenance outage is also in progress.
Yeah, so our crawler needs about 6 inches of clearance, or at least the robot itself is 6 inches. We usually look for like 7 or 8 inches of clearance. So we can get under things like scaffolding if you do have scaffolding erected. For a digester shell, we do most of our digester shells with no scaffolding at all. So what we'll do is we'll talk about this in one of the case studies. We'll actually launch the robot from the flange without putting anybody inside of it. But yeah, so 6 to 7 inches is about what we need to get under something.
Great. And then what megahertz transducer does a robot use, and how high can you go on tanks?
Yeah, so we can go about 300 feet up with our robot, and we use a variety of different sensors. So we'll use 2.5, 5, and 10 megahertz sensors depending on the specific job and the thickness of the material.
Great, that's all.
All right, we'll hop into some of the case studies here. First, we're going to go over a recovery boiler that we did down in the Southeast, where we scanned all of the water walls above the stud line. We performed this inspection in about 36 hours total. And those of you, I mean, all of you are familiar with the dangers.
An explosion damaged a paper mill and injured a worker in Outagamie County. The Kaukauna Fire Department says the explosion happened at Expera Tilmany just before 10:30 last night. It took firefighters about 50 minutes to put out the flames. A spokesperson for Expera says an explosion occurred when they were shutting the boiler down.
All right, and of course, we know that the potential for explosions and danger from recovery boilers specifically is really high. Particularly in the lower furnace, there's a lot of attention that's paid to make sure that there's not water wall leaks and there's not integrity issues within the furnace. The potential outcome of this could be serious injury, death, or destruction of the mill. And so that was, when we came to this site, that was what they were looking to avoid. And you can see what the issue that they had was here. They were faced with under deposit corrosion rather in their furnace. What they did is they had manual inspectors come in. They were taking UT thickness readings, and they cut out a few tubes with some low readings that they found. And you can see on the left side of the screen here what they found. So they found these pits that were about the size of a pencil eraser that were caused by under deposit corrosion. And they knew that this was an extremely dangerous condition if they left it unchecked. And so they brought us in to do an entire scan of the boiler because they knew that it wouldn't be possible with manual inspectors to actually get enough data to understand the extent of the issue. So what they had us do was a scan with our TOCA 4 robot. So you can see our robot running right here on the left. The robot that you see is climbing 8 tubes at one time. It's doing 3 angles on each tube as it climbs. And it's climbing at a speed of about 6 inches per second. The robot itself will generally climb between 6 inches and 1 foot per second. And we used the readings that we took here to identify these areas of under deposit corrosion within the furnace. And I know we talked a little bit about, there was a question about the frequency of the transducers. So this is a good slide for that. This is what our operators are actually looking at when they're taking readings. So you can see up top here, there's the actual A scans that are coming through, and we're actually saving and storing all of this raw data as part of the inspection. So if there's ever a question about a specific thickness reading, we can actually go back and reference an exact A scan, how we evaluated that A scan, and the thickness that came out of that. And so this ensures that you get really good accuracy all along.
Hey, David, does it work on tangent tube furnaces?
Yes, it does.
Okay. And then can you scan over paint? Do you need a specific standard for this inspection?
Yeah, so we can scan over paint, you know, depending on the makeup of it. You know, with a lot of these things, we need to just understand exactly what the composition of the material is. And it's the same thing with things like composite and overlaid tubes. So we can scan on composite tubes, on overlaid tubes in recovery boilers. The most important thing is just understanding what is the metallurgy of the composite or of the overlay. So the short answer is yes. Long answer is we would just want to make sure we understand what it is so that we can calibrate the sensors correctly.
Great. And last one is, can you inspect superheaters? Maybe just a one tube crawler.
Yeah, so we've actually used our normal crawler on superheats. What we would do, I mean, since typically they'd be non-membrane tubes, we would have to just change the configuration of the sensors. But yes, absolutely, we can do superheaters. Any other questions?
Okay. Not yet.
All right. So we'll talk through the results of this recovery boiler case study. So we collected about 12 million UT readings in 36 hours. You know, if you compare that to what a manual crew would do, a manual crew might be collecting, you know, maybe 50 to 100,000 readings in the same period of time that we collected 12 million. And we found a bunch of low areas with this potential under deposit corrosion, and 100% of those were also manually hand verified by the mill's nested contractor. So you proved out 100% accuracy on it. And so you can see what this looks like. I mean, this is kind of a scary picture. If you manage a recovery boiler, you don't want to see all of these low areas. Each one of these red spots that you see was a low reading that we found that was suspected under deposit corrosion. And so this gave the mill what they needed to be able to make the repairs to ensure that they could safely bring the recovery boiler back up. So this is an example of a recovery boiler lower furnace. This is the 3D view of it. So you can see what we have is a 3D version of the recovery boiler furnace. You can zoom in, jump around it. We can also zoom in on a specific area if we want. So we can see like just this low reading right here, tube 43, position 9. We can see the exact thickness at that area. And then also the elevation of it, 9 feet, and a picture of it. I'll actually jump to the 2D view here as well.
So everyone kind of heard the 12 million data points. Do people normally have access to all of the UT data that's collected?
Yeah, it's a good question. So I'll show you actually on this this one right here, so you can see. So what we're actually doing is we're taking those 12 million data points, and we're actually picking out for each 1 foot of one linear foot on a tube. We're picking out the low reading for that 1 foot section. So you know, we'll go back to this one, tube 43, elevation 9, thickness is 135 mils. So that 135 mils is the lowest reading we found in that 1 foot area. We can do different resolutions if you need. So we can also go down to like 3 inch, 6 inch, 12 inch, so that you get the data that you need. You know, obviously 12 million readings is not something you're going to be able to do a lot with, but knowing that all those readings were collected means that you can be certain that you didn't miss anything. And you can see we can also do things like zero in just on some low readings here. And so you can use all of these tools to analyze the data and really understand it. All right, let's hop back into the presentation here. All right, we'll jump into a second case study on batch digesters. So we've done a lot of batch digesters with our robot. The specific one that we'll be talking about right now is a batch digester that had carbon steel shell, and it had Inconel weld overlay. And so we performed an inspection on this with both UT thickness readings of the shell and also magnetic induction readings to get the thickness of the Inconel weld overlay. We completed this inspection in about 8 hours of total inspection time. The problem that we were trying to solve for the mill is that the failure of pressure vessels like digesters is extremely dangerous. I don't know if any of you have seen, but there was actually just an announcement today or yesterday of an explosion that occurred yesterday at a paper mill up in Maine on their digesters. So, you know, it really drives home that these are potentially very dangerous assets. And they also tend to be very difficult to inspect. So batch digesters in particular require vertical confined space entry. They require umbrella scaffold. You have to put people in them for longer periods of time. And then it's also difficult to get a lot of data on them in that short period of time that you have them down, because you have to take those readings manually. You have to set up the scaffolding. And so this increased downtime could lead to potential problems for the mill, such as reduced production if you have to have the digester offline for a long period of time. And so the inspection procedure that we came up with was a digester scan, an internal digester scan with no confined space entry. So we designed a procedure where we could launch the robot from the top flange of the digester, drive it down into the digester, and collect those readings on a 3-inch by 3-inch grid with no confined space entry, and handle the entire inspection in about 8 hours. And so you can see what this looks like. This was the data that we were able to collect on this particular digester. So you can see really dense data. And some things to note in this. So if you look at the 0 mark here, the 0 position, that would be where the liquor inlet nozzle is up top. And so you can see on the corrosion pattern, you have a lot more corrosion up there than you do in some other places. And so this really gave the mill all the information they needed to know where they needed to make repairs and to understand how fit this asset was for service going forward. And here's a quick video so you can see what it looks like. This is us running inside of the batch digester. You can see the green laser line. The robot is following that to ensure that it stays straight throughout the vertical run on the digester. And with this scan right here, there is nobody inside of the digester. The only thing that goes inside is the robot itself.
Have you ever scanned blow line from digesters to blow tank?
Yeah. So the robot can do piping down to about 6 inches. So we can scan blow lines. We've done blow lines. You know, specifically like the radiuses, the robot can handle those as long as they're about 6-foot radius, which coming from most batch digesters, that's what we're seeing, is that, you know, it's about a 6-foot radius coming out of the bottom of the digester. So yeah, we can absolutely do blow lines.
Great. And then how does a digester inspection differ from a storage tank inspection?
Well, you know, so, you know, digester inspection is going to be very similar in a lot of ways to a storage tank inspection. You know, the biggest differences would just be the construction, the materials. You know, typically we're not seeing storage tanks that have Inconel weld overlay on the inside. So, you know, storage tank inspections actually tend to be maybe even a little bit more straightforward than a digester inspection. But there's a lot of similarities. You know, running the shell of a digester versus running the shell of a storage tank are going to be very similar.
And then in a pipe, how does the robot handle deposits?
Sorry, can you repeat the question?
Yeah, so in a pipe, how does the robot handle deposits?
Yeah, well, so for our robot right now, we're only doing scans from the outside of a pipe, from the outside diameter. We would handle deposits in the same way that we would on a boiler tube, where, you know, we're using the UT signal and we're evaluating the UT signal with a combination of computer algorithms and then also human evaluation to understand whether or not what we're seeing from that UT signal is indicative of a bad signal versus under deposit corrosion or some sort of underside deposit. All right, we'll move on here to the future of robotic inspections. And we did get a chance to talk about a little bit of this throughout the presentation here, but there's a lot of stuff that we're working on and that a lot of other robotics companies are working on right now in terms of the future of robotic inspections. The first one being the introduction of new inspection techniques to be utilized by the robot. So right now with our robot, we handle ultrasonic thickness testing, magnetic induction, and visual. We are working on other inspection techniques such as phased array, eddy current. And, you know, for us in particular, we also do all of these other methods manually still. So all of our operators, they all run or rather they can all do manual inspection techniques like MT, PT, phased array, et cetera. But we're working on getting that stuff onto the robot as well. And then in addition to that, there's a lot of work being done in the industry right now on AI and machine learning techniques, both to analyze data faster and also to produce more relevant information. So the first thing that we're looking at is working on getting true real-time data delivery, so less processing that has to occur after we've done a robotic scan. And then also utilizing advanced techniques to be able to more easily identify difficult damage mechanisms, things like hydrogen damage, underdeposit corrosion, underside deposits, and things of that nature. And then finally, we're really focused as a company on safety, and a lot of robotics companies are really looking to make the inspection process safer by doing things like eliminating confined space entry. So right now we're able to do some of our inspections with no confined space entry. Our goal is to get to a point where eventually we can do all or nearly all of inspections without requiring confined space entry to ensure that they're being conducted in the most safe way possible. So that's all we've got for the presentation here. We'd be happy to stick around and take some more questions. Sam, I don't know if there's more questions out there.
Yeah, definitely.
Okay.
Yep. So let's get started. Just as a reminder to everyone who's still on, if you have questions, go ahead and send them through the Q&A and we'll get to them. So first question we have is, somebody already has a crew from ATS nested on site. How can robotic inspections help them?
Sure. Yeah, so there's a couple of ways. So first of all, I mean, we also do run and maintain work. So we're happy to have our crew nested on site, either in place of a typical manual inspector or in addition to them. And by having our crews nested on site, you can have access to that robot all the time. And then also our crews can still do manual inspections such as UT, PT, MT, et cetera. And we can often do this at basically the same cost as what you might be getting today from manual inspectors. So there's potential benefit there. But then the second piece would just be allowing us to handle assets that you need to do a lot of scaffolding work on, or assets that you have had trouble with in the past. So if there's something where you want to gather a large amount of data on it, that would be a good time to bring us in. And we're happy to work alongside your existing nested crews as well, and we've done that in the past. And then also for things like outage work, like recovery boilers and things like that, bringing us in to perform NDT on recovery boilers or on power boilers, where you would usually need to bring in a large number of manual inspectors, can be a great fit for the service that we provide, and can also give you a lot of information on those assets.
For an in-service pipe, what temperature can the robot handle?
So we can go up to about 250 degrees. So we talked about blow lines before. When we've done blow line inspections, we have done them online. I know blow lines can sometimes probably get a little bit above that 250 threshold. If that was the situation, we would probably just stop the inspection while the digester is blowing out to the blow tank, and then we would continue it when that was done. But yeah, so 250 degrees is the official limitation right now. And so it gives us the ability to probably handle just about any asset that you have at a paper mill, even while it's online.
Do you have API inspectors?
Yeah, we do. So we have API inspectors on staff, so we can perform 653, 510 inspections for you with robotics.
Transition from vertical to horizontal walls?
Yeah, so depending on the angle, we can make those transitions with the robot. So basically what the robot will do is it'll lift up the sensors, it'll make the transition, and it'll put the sensors back down. It really does depend on the specific angle. So, in a lot of PC boilers in the power industry, we make the transition from the slopes to the vertical walls with no problem. With recovery boilers, I would assume this is related to the nose arch and getting onto the nose arch. There are some times where we can make that transition, and there's some times where we can't. So we would just need to look at the specifics of it. I mean, this kind of goes back to this idea of being really prescriptive about what you're doing with a robot. What we would need to see is kind of a drawing of the boiler so that we can evaluate whether or not the robot can actually make that transition. If it can't make the transition, it doesn't mean that we can't run it. It just means that we would need to have access to be able to place the robot. So there are a number of potential methods for doing that. So a lot of mills will use sky climbers, so they don't have to scaffold the entire boiler. They can get us up to a place where they can place it. And there's also actually been some discussion about from a dance floor, actually cutting a hole in the dance floor and placing a hanging scaffold underneath it so that we could place the robot. So there's a bunch of different potential options if we can't make the transition.
How tight of a radius or bend in the pipe can the robot handle? For example, around a pipe fitting?
Yeah, so well, there's really two answers to that. The current robot that I showed you here, we can do about 6 foot bend radius. We do have a new robot in development right now, which is supposed to be available this fall, that will be able to make much tighter bends. So even up to like 90-degree bends over 18 inches, 10 inches. I think it's going to go down to 10 inches for the radius, but don't quote me on that. I'd be happy to follow up later on with whoever asked that question if we have their name, and we can get the exact information on it.
Definitely. How are surfaces prepped to capture accurate UT readings?
Well, and a lot of this is going to depend on the specifics of the asset, but normally what we're going to do is we're going to see places doing a water wash to clear away any debris. So for a recovery boiler, for example, a water wash is going to be sufficient to get it clean enough. So we couple to the wall for UT readings with water. So we use a water column UT sensor. Because of that, we're actually going to clear off a little bit of debris with the water that we're using just in the process of the inspection. So we're able to get accurate readings on surfaces that are much dirtier than what you might expect as compared with manual inspection. Now, that being said, there's going to be a direct correlation between how good the data is and how clean the surface is. So we do still require that surfaces be cleaned prior to performing inspections, but the specifics of how clean it needs to be, that's really kind of the type of thing where we need to maybe see pictures or, see the asset in person to understand exactly whether or not you would need to do more cleaning or less cleaning or what.
So what if a tank is insulated but has a sheet metal cover?
Well, so if a tank is insulated, we're not going to be able to collect UT readings on it. I mean, just like you wouldn't be able to collect UT readings on it with insulation right now. The options there would be, for an insulated tank, run it internally or cut out strips of insulation so that we can set the robot on it. So, it's really going to be dependent on the specific situation and the scope of exactly what sort of information you're trying to gather. But yeah, to run it externally, we're going to need access through the insulation in order to get those UT readings.
Great. Right now, that's kind of all the questions we have. We'll wait a couple more minutes here in case anybody has any last minute questions they want to submit. But otherwise, we'll also be emailing the recording of this webinar to everyone as well, in case you want to share it or rewatch it. And then if you have any other questions or want to talk to David personally, his email is right on the screen there. Feel free to reach out.